The study of surface characteristics is a broad category of Mars science that examines the nature of the materials making up the Martian surface. The study evolved from telescopic and remote sensing techniques developed by astronomers to study planetary surfaces. However, it has increasingly become a subdiscipline of geology as automated spacecraft bring ever-improving resolution and instrument capabilities. By using characteristics such as color, albedo, and thermal inertia and analytical tools such as reflectance spectroscopy and radar, scientists are able to study the chemistry and physical makeup of the Martian surface. The resulting data help scientists understand the planet's mineral composition and the nature of geological processes operating on the surface. Mars' surface layer represents a tiny fraction of the total volume of the planet, yet plays a significant role in the planet's geologic history. Understanding physical surface properties is also very important in determining safe landing sites for spacecraft. Like all planets, Mars reflects a portion of the light it receives from the Sun. The fraction of sunlight reflected is a quantity called albedo, which ranges from 0 for a body that reflects no sunlight to 1.0 for a body that reflects all sunlight. Different parts of a planet's surface have different albedo values depending on the chemical and physical nature of the surface. No topography is visible on Mars from Earth-based telescopes. The bright areas and dark markings on pre-spaceflight era maps of Mars are all albedo features. They have little relation to topography. Dark markings are most distinct in a broad belt from 0 degrees to 40 degrees south latitude. However, the most prominent dark marking, Syrtis Major Planum, is in the northern hemisphere. Outside this belt, the classical albedo feature Mare Acidalium is another prominent dark area that lies north of the main belt. Bright areas, excluding the polar caps and transient clouds, include Hellas, Tharsis, and Arabia Terra. The bright areas are now known to be locations where fine dust covers the surface. The dark markings represent areas that the wind has swept clean of dust, leaving behind a lag of dark, rocky material. The dark color is consistent with the presence of mafic rocks, such as basalt. The albedo of a surface usually varies with the wavelength of light hitting it. Mars reflects little light at the blue end of the spectrum but much at red and higher wavelengths. This is why Mars has the familiar reddish-orange color to the naked eye. But detailed observations reveal a subtle range of colors on Mars' surface. Color variations provide clues to the composition of surface materials. The bright areas are reddish ochre in color, and the dark areas appear dark gray. A third type of area, intermediate in color and albedo, is also present and thought to represent regions containing a mixture of the material from the bright and dark areas. The dark gray areas can be further subdivided into those that are more reddish and those less reddish in hue. Reflectance spectroscopy is a technique that measures the amount of sunlight absorbed or reflected by the Martian surface at specific wavelengths. The spectra represent mixtures of spectra from individual minerals on the surface along with contributions from absorption lines in the solar spectrum and the Martian atmosphere. By separating out each of these contributions, scientists can compare the resulting spectra to laboratory spectra of known minerals to determine the probable identity and abundance of individual minerals on the surface. Using this technique, scientists have long known that the bright ochre areas probably contain abundant ferric iron in mafic minerals and show absorption bands suggestive of pyroxene, a group of minerals that is very common in basalt. Spectra of the redder dark areas are consistent with mafic materials covered with thin alteration coatings. Thermal inertia measurement is a remote sensing technique that allows scientists to distinguish fine-grained from coarse-grained areas on the Martian surface. Thermal inertia is a measure of how fast or slow something heats up or cools off. For example, metals have very low thermal inertia. An aluminum cookie sheet taken out of an oven is cooled to the touch in less than a minute, while a ceramic plate taken from the same oven takes much longer to cool off. Scientists can estimate the thermal inertia on the Martian surface by measuring variations in surface temperature with respect to time of day and fitting this data to numerical temperature models. The thermal inertia of a material is directly related to its thermal conductivity, density, and specific heat capacity. Rocky materials do not vary much in density and specific heat, so variations in thermal inertia are mainly due to variations in thermal conductivity. Solid rock surfaces, such as outcroppings, have high thermal conductivities and inertias. Dust and small granular material in